All right, so guys, what we're going to do today is we're going to talk about reaction rates. The date today is the 30th if you want to date your notes. And guys, it's going to be important for you to sort of understand how this material doesn't fit into what we did previously. So once you're all settled in, I'll sort of give you a sense of where this fits, because it doesn't naturally fit yet. And then we'll get you going and get this in your brain. And then, guys, you're going to do a lab on Wednesday, which I really think you're going to like, which is the follow-up on this. So you guys ready to go? Okay, so here's the deal, guys. Last time in class, last Thursday, we talked about acids and bases, right? And you learned about proton exchange and conjugates and pH and all this other stuff. So you're naturally thinking, when we get into class today, we're going to build on that and we're going to talk more about acids and bases. We're not until Friday. Here's what's going to happen. Today, guys, what we're going to do is we are going to talk about how fast reactions go. And we call that reaction rate. Rate or speed is a measure of how quickly something's happening. So guys, today we're going to talk about reaction rates. And then on Wednesday, guys, we're going to go into lab with almost no procedure. What we're going to do on Wednesday is I'm actually going to teach you very quickly how to do a simple reaction. It involves a solid and an acid. And you're going to go into lab and you're going to do this reaction and you're going to time how long it takes for the reaction to take place. And then, guys, you're going to run the reaction 3 more times. And every time that you run the reaction, your goal, without any leading from me, your goal is going to be to get that reaction to go faster 3 more times by changing 3 different variables, 1 each time. And then you're going to actually, after writing your own procedures, you're going to do those reactions 3 more times, time them with a stopwatch, and make sure they're going faster. You get the idea? So what you're going to learn today is, first of all, what is it that determines how fast a reaction goes? And then you're going to learn how to make it go faster. And then, guys, what's going to happen on Friday, we're going to pull this all together and we're going to talk about how fast acid-base reactions go. And that's how this fits in, but that won't be till Friday, which will be Spirit Bowl and good stinking night. We're going to struggle to get anything done, right? All right. Although, here's the really nice thing about Spirit Bowl. Mr. Rep actually sent me an email over the weekend asking me to order all of the stuff for Spirit Bowl because I have connections with Amazon, and the order that he sent me was so completely messed up that I couldn't place the order. So you may have to pretend that people look like Gandalf because he may not have any of the costumes. We'll see. So, all right. So, guys, let's get started here. What we've got to do to get going is we've just got to get some terms in your brain. So you need to write these on your paper so that they also then get in your brain. So guys, in order to get started, there are some words that you need to be able to handle intelligently. The first of those words is the word magnitude. Now guys, I'm guessing that magnitude is not a word that comes out of your mouth very frequently, so we'd better talk about what it means. So guys, when we talk about magnitude, the only place in my world where I know about magnitude is earthquakes, right? And so remember that horrible tsunami that wiped out the east coast of Japan? I don't know if you remember that. But guys, that was like a magnitude. Do you remember the magnitude of that? It was like 7, was it? Okay. So they said that was a magnitude 7 earthquake. Of course, they don't give you units. But guys, magnitude 7 is actually measured on something called the Richter scale, which is actually named after this geologist named Richter that pulled it together. But guys, when we talk about magnitude in that or any other setting, what it simply means is the amount of energy that an event possesses. So there are some units, although maybe it doesn't have units, but when we say magnitude 7, that is telling us how much energy was involved in that earthquake. Okay, so first term is magnitude. Next term, frequency. This one I'm guessing you probably have a better sense of. What does frequency talk about? How often something happens, right? Frequency talks about how often an event occurs. And then guys, this seems kind of weird. The next term that you need to know is actually the topic for the day. It's not something we're going to build into. It's something we're just going to lay out there and then we're going to pick apart as we go. But guys, the third term that you need to know is reaction rate. So when we talk about reaction rate, we talk about the speed at which a reaction progresses. Now guys, for those of you that have been in physics, you know that rate and speed and velocity don't mean the same things, but for our purposes, we're going to treat them as being interchangeable. So guys, when you think about speed, what do you think about? How fast something goes, right? But what's that thing in your world that you worry about its speed? Your car. And so guys, when we talk about the speed of your car, we understand the units. If we say we're going down the street going 30, we all understand we mean 30 miles per hour, right? So guys, we know that one unit for speed is miles per hour. What are other things that we know the speed of or measure the speed of, and what are the units? Okay, what about this? Some of you are going to learn something. When you look down at your dashboard, many of you have two needles. One of them tells you how fast you're going. What does the other dial tell you? RPMs, right? The speed. It's called a tachometer. And guys, it tells you the speed at which your crankshaft is spinning, but it's a measure of how fast your engine's going. And what are the units for the speed at which your engine's spinning? RPM, which are revolutions per minute. Now guys, think about this. Your car is traveling in miles per hour. Your motor is spinning in revolutions per minute. What do those two units have in common? Time, right? Miles per hour, revolutions per minute. Guys, the common thread is time. And guys, all units of rate have got to have time. So when we talk about the rates of reactions, it's got to have time. But what's the thing we're measuring over time? And the answer is moles of product. So when we measure the rate of the reaction, it will be, the units will be how many moles of product are produced in a unit of time. But guys, what would a reasonable amount of time be to measure the rate of a reaction? Hours? No, way too long, right? Minutes? I'd go with seconds, because guys, even minutes are too long. So these are going to be our units for rate, moles per second. Hours and minutes are just way too long. Reactions happen many times on the order of fractions of seconds. So we're going to go with moles per second. All right, you guys all caught up with me? You good? You ready? You understand magnitude is the amount of energy, frequency is how often, and then reaction rate is how quickly a reaction takes place. Groovy? Groovy. All right, so guys, pay close attention to these pictures. Because you're in this class, you're getting smarter. Because you're getting smarter, you should be able to think like a chemist about this. It's a fireplace. Guys, what's going on in that fireplace? What kind of reaction is this? It's a chemical reaction. Yeah, what kind of chemical reaction? It's a combustion reaction. Guys, we're reacting with oxygen, and what are the things that are being produced then? Carbon dioxide and water. Where does the water go? It immediately boils. But guys, this is a combustion reaction. There's all sorts of hydrocarbons and carbohydrates, which then makes it technically not combustion. But guys, this is a combustion reaction, and we're releasing carbon dioxide and water as this reacts with oxygen. Now guys, what about this? What's going on here? So what's happening to this? What is this made of? And okay, so where did I get the picture? I actually found this big high-res picture of this beautiful barn out in the middle of a hayfield in Kentucky. And I zoomed in on it, and I found this rusty iron ring where they would tether horses up to the side of the barn. And you can almost imagine 150 years ago, some old settler all excited, he finally got his barn built, and the last thing he did was hammered in the ring, right? But guys, what did that ring look like 150 years ago? Maybe shiny, certainly black. We had blacksmiths back then. It certainly didn't look like this, because what's been happening to it for the last 150 years? It's been rusting, it's been oxidizing. So guys, here's the question that I have for you. What is this reaction, the rusting of iron, and this reaction, the burning of hydrocarbons, what do they have in common? They're both reactions with oxygen. They don't both involve water. This doesn't produce water. But guys, these are both reactions with oxygen. They're both oxidation reactions. So guys, here's the question. Why does this go so stinking fast that if you came back in the morning, well, let me ask you, if you came back in the morning, what are you going to see? It's not going to be fire anymore. It's going to be ash. The reaction's over. Why is the reaction over? Let's see if you learned anything last unit. Why is the reaction over? Limiting reactant's gone. Which is the limiting reactant? The wood, right? Okay, so that one's done. But guys, if you came back in the morning and found this, what's it going to look like? That, right? It would actually have a little bit more rust on it, but it would be almost imperceivable. So guys, both of these are reactions with oxygen, but why does this one happen so fast and this one go so stinking slow? Well guys, that's what we're going to talk about today. I'm not going to give you the answer now, but the very last slide today is going to be this picture again, and you'll be able to answer the question because you will know what determines the rates of reactions. So guys, again, the question that we're going to answer today is this. What is it that what has to happen in order for any reaction to happen, whether it be fast or slow? Because if we can figure out what has to take place, we can then figure out how that's different for fast reactions and slow reactions. And then we'll come back and answer the question. You get it? Okay, so here we go. This is where you need to start taking notes again, guys. This is bottom line. What has to happen for a reaction to take place, whether that reaction is going fast or whether that reaction is going slow? And guys, the answer is simply this. It's called the collision theory of reaction rates. And guys, the bottom line is this. In order for wood to react with oxygen, what has to happen given what you just wrote down? What has to happen with the wood and the oxygen? They have to collide. And guys, in order for iron to react with oxygen, what has to happen? They've got to collide. Guys, if the oxygen doesn't run into the wood or the iron, they can't react. So there has to be a collision in order for the reaction to take place. Guys, it's that straightforward. It simply says that for a reaction to take place, a collision must occur between the reactants. Now guys, this is where this gets interesting, because it turns out that they've got to collide with a fair amount of energy. If they just bump into each other, they are not going to react. They have to actually collide hard enough that the bonds within the reactants break. And guys, if they don't collide with enough energy to get those bonds to break, a reaction will not take place. So when the iron and the oxygen, well, let's do the wood. When the wood and the oxygen collide, they've got to collide hard enough that all the carbon and all the hydrogen in the wood break apart into carbons and hydrogens, and the O2 breaks apart into oxygens. And if they collide with that much energy, then the carbons and the oxygens and the hydrogens can all reorganize and form water and carbon dioxide. But guys, the trick is this. Not all collisions are effective. If they don't hit hard enough, nothing happens. No reaction will occur. Am I going too fast? You guys okay? So guys, you don't need to write this next point down, but this brings up sort of an obvious question, right? If these things have to collide in order to react, and if not all collisions are effective, then the obvious question out there, right, is how hard do they have to collide? How hard do these things have to run into each other in order for the reaction to take place? Are you guys ready to transition with me? Is that okay? So how hard do they have to collide? Guys, the answer to that is this, and this is the big important idea of the day. It's called activation energy. So guys, what is activation energy? I'm going to define it, and then I'm going to help you think about it in a way that'll actually really help you. So guys, activation energy, by definition, is the minimum amount of energy needed for a reaction to occur. Now guys, this next bullet point you don't need to write down, but it leads into the analogy, but the third one you do, and then we'll talk about the analogy. So here's what we know. We know that in order for a reaction to take place, there's got to be collisions, but not all collisions are hard enough to make the reaction go. So how hard do they have to hit? The answer is activation energy. What is activation energy? It's the minimum amount of energy that they've got to possess when they collide. Now guys, and again, don't write this down. You can think of this as if it's a hump that exists between the reactants and the products. And the bottom line is this: the more collisions that get over the hump, the faster the reaction can go. So what does all of that mean? You probably don't even need that. Well, maybe you do. It's up to you. That one may be worth getting in your notes. This idea that the more collisions that get over the hump, the faster the reaction goes. You guys all caught up with me? We're going to stop taking notes for a minute and help you understand this. So catch up, and then we'll explain it to you. And then we'll apply it to reactions. You good? So guys, you've all been up on 8th North, right? Cascade Golf Course. Used to be Cascade Golf Course. Now it's somebody's backyard. But thankfully, they didn't mow down the putt-putt course, right? Are they going to? I hope not. It's a lovely place for a first date. So guys, have you all played this hole at either the Cascade putt-putt course or any other putt-putt course in the area? You guys know about this hole, right? Guys, and I mean guys, I don't mean girls and guys. Guys, you do not want to play this hole in the presence of a date, right? Because what is it that makes this hole so stinking hard? It's a finesse issue, right, guys? And the problem is, and the thing that they don't show you is on the Cascade course, there's a cliff here. Well, not really. But if you overshoot the hole, you get into all sorts of trouble over here. So you know how this goes, right? You can picture it. You've got that stupid little putter that's about 6 inches too short, that's got sort of like that pseudo metal head on it, right? And you've got that orange or red golf ball that used to be round, but now it's more like an egg, right? And you come up here to play the hole, and you stand up at the hole, and do you love that they give you a mat that has the 3 little places you can put your ball as if it matters? You know what I'm talking about? And so you actually stand there and think, which one of these holes is going to be the best place to put my ball? It doesn't matter. You can actually pick up the whole stinking mat. But so you put your ball in just the right hole, and you get up here, and you know your date's watching, right? So this has got to be good. And you come back, and you want to actually look like you golf, right? So you actually want to hold the putter right. You can't just get up there and manhandle it like a baseball bat. You got to do the thing with your fingers. And you get up here, and you come back, and you're thinking Tiger Woods, and you come back, and pink, and you hit the ball, and you know what happens, right? So this ball comes, and it rolls, and it rolls, and it rolls, and it gets to about right there, and it stops. And then what happens? The ball ends up where? Sometimes even right back in the same stinking hole at your feet where it started, right? And you're hoping nobody saw it, and you're hoping you don't have to count the stroke, but you feel like an idiot because you didn't get over the hump, right? So then you decide the next time, all right, I got this. And you get up here and you really have you ever done this? You can actually do this at the Cascade course. If you hit it hard enough, the way this hole's lined up, you can actually launch your ball into 8th North. Have you ever played that? Yeah, it's lined up, and if you hit it hard enough, it can end up at that rehab center over where the Osmond's place used to be. But anyway, you get up here and pink, and you hit the ball. And guys, what happens if the ball makes it to here? Right to there. Well, let's make it a little more, right to here. Your money, right? Guys, if you can get the ball to here, that ball is going to roll down the backside, and you pray you didn't hit it so hard that it goes past the hole. But guys, as this applies to chemistry, here's the thing that's cool. Once the ball gets over the hump, there are no hazards over here. Every ball that goes over the hump goes into the hole. So, with that as an analogy, guys, how does this apply to chemistry? Well, you got to understand there's a little problem with the analogy. In order for this to work in chemistry, here's how it have to go down. You'd have to put your ball down, hit it, and so the ball is one reactant, right? You'd have to hit it with the putter, don't try this, and then let go of the putter and have the putter and the ball stick together and fly over the hump and go into the hole, okay? That's not going to happen. But guys, the idea is this. In chemistry, we have collisions as well, like the ball with the putter. And when the ball and the putter hit, they have some energy, and they can go literally uphill as far as energy goes. And if they make it to the top of the hill, they will roll into the cup. Now guys, if they don't hit with enough energy to make it over the hump, they come back down and it's as if nothing happened at all. So guys, what do we call this hump in chemistry? Activation energy. So here's the question then. You ready? What if we want to take reactants and turn them into products, and we want to get as many balls in an amount of time? We're talking rate, right? So amount of time. What if we want to get as many balls as we can into the hole? And remember, in chemistry, all they've got to do is go over the hump and they automatically go in the hole. So guys, if we want to get dozens of balls in that hole really fast, what are we going to do? Well, let's think about it. So we grab a ball, say we got a bucket of putt-putt balls, right? And we grab a ball and we sit it down and we go, tink. Is that going to work? What do we want to do? We want to whack the crap out of that ball, right? Right. And in chemistry, we don't call it whack the crap out of. What do we call it? What's the word you learned at the beginning of the day? Magnitude, right? We want to hit that ball with a huge magnitude. We want to be like, crack. Because guys, in chemistry, the ball can't fly over to the rehab center. If it makes it over the hump, it will go in the hole. So crack. But guys, what about this? Do we want to go put the ball down, crack, sort of stretch, and then put another ball? What else do we want to do if we want a bunch of balls in the hole? It's like a machine gun, right? You're like down and cracking, down and cracking, down and cracking. And what do we call it if we have something going really fast? It's got a high frequency. So guys, that's the idea. In order to make a reaction go faster, we want those collisions to happen hard and often. And that makes the reaction go faster. Do you understand the idea? So the faster the reaction is, the harder and the more frequently they're colliding. Now guys, with that as a background, you need to write this down. And guys, make it about 3 inches by 3 inches in your notes. This is the way we represent this concept graphically. The y-axis is energy. The x-axis is time, or reaction progress. And then guys, the idea is this. Over here on the left, we have reactants. And in order for those reactants to create products, they've got to collide. But they've got to collide with enough energy to get over this hump. And if they don't make it to the top of the hump, they will not stick. They will not turn into products, and they'll just end up back at your feet as if nothing happened. Now guys, let's sort of take this out of the conceptual and into the practical. So let's make it a single displacement reaction. A plus BC. Remember, A is an element, BC is a compound. And guys, let's say that A is a metal. So if it's a metal, what's its charge? Positive or negative? A is a metal, so it's positive. So guys, if A is a metal, will it hook up with B or C? Remember, single displacement reaction, does it go to B or C? C, right? So our products are AC plus B. So guys, in order for this reaction to take place, what has to happen? Who has to collide? A and BC. And how hard do they have to collide? The answer is this hard, and we call that activation energy. But guys, what is that the amount of energy necessary to do? That's the amount of energy necessary to bust B and C apart. So when these things collide, A has got to hit BC hard enough that BC breaks apart. That's this amount of energy. And if BC gets hit hard enough that it breaks apart, then A can hook up with C and it just rolls down to products as B is given off. But guys, if A and BC don't hit that hard, then BC doesn't break apart and it's as if nothing even happened. You get the idea? Okay, and again, guys, that hump is called activation energy. So you good on the idea of collisions and activation energy? Okay, so guys, you may want to be careful taking notes as we move forward because I think you already understand this, but let's try this out. Okay, so here's the idea then, and it's sort of review. Again, if you want to get this in your notes just sort of as a summary, this is the idea. Guys, for a reaction to go faster, what has to happen is we've got to have more reactions that get over the hump. So again, guys, how can we do that? How can we get more reactions over the hump? Well, we said it's two things, right? Magnitude and frequency. So if we can increase the magnitude of the collisions, we can get more collisions over the hump. Or if we can increase the frequency of the collisions, we can get more collisions over the hump. So guys, that's it. That is the fundamentals of reaction rates. In order for a reaction to happen, what has to take place? They've got to collide. But just colliding isn't enough. They've got to collide hard enough to get over the activation energy hump. So what can we do to make sure that more collisions get over the hump? We can make them collide harder, or we can make them collide more frequently. Either one of those will get more collisions over the hump, just like hitting balls over the thing in the putt-putt course. And the more collisions that get over the hump, the faster the reaction goes. You guys good on theory? Do you have anything you want to talk about? Okay, so guys, this is about to get wildly practical, and these are the things that you've got to pay attention to in lab. What we're really about to do is give you all the procedures for the lab on Wednesday, because what we're going to talk about now is this. How do we do this? How do we make them hit harder? How do we make them hit more frequently? Because I don't ask it rhetorically. What can we do to make them hit harder or more often? So speed them up. And how do we speed them up? Heat them up. Go ahead. Well, good, yeah, so warm them up. So guys, if we warm them up, we'll speed up the reaction. What else? Yeah, one of the things we can do is grind them up. And guys, understand that we're going to go through each one of these individually. So that's actually 2 of the 4. We can heat them up, we can grind them up. What else can we do? Do you know? No, cool them down actually makes them go slower. It's the inverse of heat them up. Go ahead, Will. It's an example of something that you've probably not thought of this way, because when you, did you see Will's example that if you've got, like a true Boy Scout, if you're trying to get a fire going, interestingly, you start it in tinder, right? And you've got that little ember and it's glowing, and you pick it up like a delicate bug, right? And you don't want to squish it, and you start to blow on it, right? Guys, why do you blow on the fire? It adds more oxygen. What you're actually doing is increasing the amount or concentration of the oxygen. So guys, to your credit, you got 3 of the 4. You got temperature, you got surface area, you got concentration. I'll give you the 4th. It's the last one we're going to talk about. Add a catalyst. And we'll talk about that last. So guys, let's pick these off one at a time. You want to put these in your notes because this is the foundation for your lab. So guys, we're going to go temperature first. So let me restate what you already know. Ready? Bottom line. Temperature goes up, rate goes up. You could just write that. Temperature goes up, rate goes up. Let's actually just write. Oh, no, I don't. I would just write that. I'll change my notes later. Temperature goes up, rate goes up. Guys, do y'all understand that this is why you all have a refrigerator at home? Because if increased temperature makes the reaction rate go up, what does decreased temperature do? Makes it slow down. And what reaction are you trying to slow down when it comes to your food? Rotting, right? So you take your food and you put it in a fridge, it slows down, it cools it down, and it allows it to rot at slow enough a rate that you can eat it before it's so nasty that you would die if you ate it. But guys, understand, when you put your food in the fridge, it is still rotting. It's just rotting slowly enough that the rot hasn't taken over and you can eat it before it's done. But your food is always rotting. You're just slowing down the rate at which it's rotting. Okay, so guys, here's what we're going to do for each of these. I'm going to give you the factor, I'm going to give you the bottom line, and then guys, I'm going to ask you a question. And it's always going to be this question. Why? Why does heating something up make it happen faster? I wouldn't write down the question, but guys, you understand it's got to be one of two factors, right? How hard, which we call magnitude, or how often, which we call frequency. Write them both down. It's either a factor, a question of frequency, or it's a question of magnitude. Because those are the two things that influence how fast a reaction goes, right? The collisions have got to go over the hump. To get them over the hump, they either hit harder or they hit more often. So guys, which one is it with temperature? Hold on a second. Let's make sure we're on the same page. So guys, for you to intelligently answer the question, is it a matter of frequency or magnitude, you've got to understand something fundamental about hot and cold. Okay, so how is hot different than cold? Well, if you have a substance that's cold, what are the particles doing? Moving. See that slowly. See the slow turtle? Okay. Now guys, what if it's hot? It is moving fast bunny rabbit, right? That guy scares me because I think he's naked. But you get the idea. So guys, if something's moving, if it's hot, it's moving fast. If it's cold, it's moving slow. You guys sold on that? So guys, why would making something hot, why would that make it react more fast, more quickly? What does it do to the collisions, David? Makes them move faster, but remember, it's not just the faster, it's how they collide. So if they're moving faster, do they collide harder or do they collide more often? Yes, right? If they're moving faster, they will collide harder, which is a question of what? Magnitude, and more often, which is a question of frequency. Now guys, if you don't believe me, remember I grew up in Wyoming, right? We spent a lot of time at county fairs. It's kind of what you do in Wyoming in the summer. Have you guys ever seen a demolition derby? Right? Where it was actually fun. I used to work at a Skidoo snowmobile shop, and every year we would enter a car in the demolition derby. So we go down to the used car lot. We'd pay like $300 for a used car. And it was a dream for a 14-year-old because they actually just gave me a sledgehammer and said bust out all the windows, because you can't have windows in a demolition derby car. So literally I just got to crack on these windows. And then we would pull out all the seats but the driver's seat. We would take the gas tank out from underneath the car and put it in where the back seat used to be, because you can't have it hanging in the back by the trunk, because if you get hit there it could explode. And then we'd weld all the doors shut, and that was our demolition derby car. It was a ton of fun. I didn't get to drive, I was 14, but it was fun to build. And so, but guys, you know demolition derby, right? There's a lot of collisions. They turn all these cars out into where eventually they're going to do the rodeo, and it's full on last man standing. People are just running into each other, right? Now guys, imagine if they set a 2-mile-per-hour speed limit in the demolition derby. Everybody's going to go home, right? Why? They're not going to run into each other very often, and when they do, it's not going to be very spectacular, right? So slow things don't hit often and they don't hit hard. But guys, that's not the way this works. You get these cars going 30, 40 miles an hour in the span of this little arena, and good night. When they hit, it's crazy. But they also hit very often. Do you understand the analogy? So guys, hotter things do hit more frequently, so circle it. It is a question of frequency, but they also hit harder, so it's also a question of magnitude. You sold on that? And guys, a little foreshadowing for the lab. Temperature is the only one that lets you double dip. Temperature is the only factor that increases the frequency and the magnitude, so it's therefore the factor that gives you the best return on your change. Yeah. No, it's not. See, when we think generically about the term catalyst, we think about just something that causes something to happen. Catalyst in chemistry has a very tight definition, and heat is not a catalyst. A catalyst is a substance. It's an element or a compound, and we'll talk in a minute. So guys, you sold on temperature? Okay, what was the next one that we mentioned? I think, Brian, you might have mentioned it. Was it Brian? Yeah, okay. So guys, the next one, oh wait, sorry, concentration's next. Never mind. My bad. We'll come back to Brian. So guys, number 2, concentration. So bottom line is this. Concentration goes up, rate goes up. You don't have to write all the words increasing. Concentration goes up, rate goes up. But again, guys, the question is why? Is this a difference in frequency or magnitude? We're going to talk. But first we got to set the stage. So you ready, gang? In order for you to understand concentration, consider these 2 gatherings of people. This is Cornhusker Stadium, Saturday, sometime September through November. This is actually a plaza in downtown Chicago, sometime probably midday. Now, guys, the question is this. If we're looking at the number of people, which one's more concentrated, the plaza or the stadium? Stadium, right? Now, if you're in the stadium, you're going to run into people more, right, than if you were in the plaza. Here we're more spread out, and the likelihood of people running into each other is less. Here, we're tightly packed together, and the likelihood of them running into each other is obviously more. So guys, here we're going to have more collisions. So is that a question of frequency or a question of magnitude? It's a question of frequency. When you're more tightly packed together, you're going to run into people more often. Similarly with chemicals, the more tightly packed they are, the more frequently they'll collide. Good? All right, so now we're going to combine what Brian said with what Will said, thinking about starting a fire. I know Will's example was relative to concentration, but he thought about this idea of starting a fire, which was cool. So let's talk about the third factor, surface area. Guys, bottom line is this. Surface area goes up, rate goes up. Again, the question is why? Is it frequency or magnitude? So guys, when I started thinking about surface area, like Will, my brain went to fire, starting a campfire. His was relative to concentration, blowing on it. Guys, my brain went here. Imagine that we want to start a fire. You're a Boy Scout, you're getting one of your merit badges, and it's time to start a fire. You're going to start here. Guys, imagine if you were a Boy Scout and they said, here, start a fire, here's a log, here's a match. You don't want to be the idiot that's holding the match to the log. It's not going to light. So guys, hopefully, and I understand that in Utah County, because most scoutmasters actually don't like being outdoors, and they only do it because it's their calling. But guys, if you actually have a scoutmaster that knows something about being outside, they probably brought and maybe trust you with axes, right? I know, this is Utah County Boy Scouts. But guys, if that's the case, what are you going to do to the logs before you try to start the fire? You're going to chop them up into kindling, right? And when you chop them up into kindling, you've got a much better chance of starting a fire. Why? It's all surface area, guys. Think about it. Every time you take one of these logs and split it, what you're doing is you are exposing a surface that was not exposed previously. And every time you cut, you are increasing, sometimes even exponentially, the amount of surface area. And guys, all that additional surface area, especially when you get these little rough fibers, guys, it's that surface area that provides more surface where the oxygen in the wood fibers can contact, and that allows the fire to actually start. So guys, which one is that? Does that mean that the oxygen in the wood hit more frequently, or does it mean they hit harder? More frequently, right? And that's a matter of frequency. You guys, again, forgive me if I insulted any of you relative to the Boy Scouting comments, but you got to understand, I grew up in Wyoming as a Boy Scout, where my Boy Scout master was ex-Green Beret, and we actually used to go jackrabbit hunting with machine guns, okay? So, yeah, Boy Scouts in Wyoming is a little different than here in Utah County. So, I have a different frame of reference. So, guys, you all set here? You good? Yeah. Okay, so the idea is this. Imagine that you're an oxygen molecule in the air and you're trying to run into the surface of the wood to start a fire. Well, on a log, there's very limited surface area. There are very few places where you can run into the wood. But imagine if you just took that one log and split it into 20 little pieces of kindling. Now, there's so much more surface area that those oxygen molecules can collide with the surface much more frequently because there's literally more surface for it to collide with. Is that okay? You guys good? Okay, so David, here you go. Last one, catalyst. So guys, I'm really glad that David asked the question that he did, because he said, wait, I thought temperature was a catalyst. And guys, maybe he's thinking about the idea that to get a fire started, you need a match. That doesn't make it a catalyst. It does get the fire started, but guys, you ready for this? What is the match adding to the system? Activation energy. Think about that. That initial little bit of heat from the match actually excites enough of the molecules that it can get over the hump. Then, once enough of those get over the hump, as they react, they release energy. It's exothermic, and that energy goes to get more over the hump. So that match actually adds activation energy. It's not a catalyst. So let's talk about catalysts. Guys, a catalyst, and this you need to know, I would write it down. A catalyst is a substance that increases the speed of a reaction. It's not energy. That was actually a question on 2 years ago's AP test. It said, agree or disagree with this statement. A catalyst causes a reaction to go faster by adding energy to it. 60% of AP students got that question wrong 2 years ago. They said, yeah, if the reaction goes faster, it's got to add energy. Guys, that is not true. Catalysts are not energy. Catalysts do not add energy. Here's the thing that's crazy. Catalysts make a reaction go faster, and they don't increase the frequency, and they don't increase the magnitude of a reaction, of a collision. Now hold on. I thought we just said that for a reaction to go faster, they've got to hit harder or they've got to hit more often. And that's true. But now you're telling me that a catalyst makes a reaction go faster and it doesn't change either one of those things. It's also true. What are we missing? Guys, how can it do that? Yeah. Drops the hump. It drops the hump. Guys, think about it. If there's a hump that keeps us from getting to the other side, one thing we can do to get over is we can hit harder and we can hit more frequently, but the other thing we can do is drop the hump. And if we drop the hump, then the collisions that are already taking place have a greater chance of getting over. So guys, what a catalyst does is it creates a pathway with a lower activation energy. It literally drops the hump. So guys, do this. Go back in your notes to this diagram. So guys, in order for this reaction to happen, we said this was A plus BC. These have got to collide and get over the hump. Now guys, what would this diagram look like? And I want you to draw it in your notes. What would the diagram look like if you added a catalyst? Draw in your perception of what this diagram would look like if you added a catalyst. And then I'll show you what it looks like. Because what would it look like if you added a catalyst? Do the reactants still start here? Yeah. Do the products still start here? Yeah. Or end up here? Yeah. But guys, the difference is, as Sydney said very well, the height of the hump. It goes like this. Guys, when you add a catalyst, it drops the height of the activation energy hump. It's like this. Imagine if you wanted to get from, I don't know, here to Strawberry Reservoir. And you didn't go up through Heber, you went over Y Mountain. You guys know that? That basically, if you go over Y Mountain, you can very quickly end up at Strawberry Reservoir. Well, guys, Y Mountain is the hump. But what if they dug a tunnel? Now you don't have to go over the hump anymore. You still start in Orem and you still end up at Strawberry, but you don't have to go over the hump anymore. You can cut through it. And guys, that's what catalysts do. Catalysts provide another way to get from reactants to products that involves less energy, and as a result, it makes the reaction easier. You okay? Okay, so guys, let's come back and let's answer our question and call it a day. Given everything that you now understand about reaction rates, why? Why does burning go so fast and rusting go so slow? Fundamentally, what has got to be different about these reactions? Say it again. Is that, I don't even know who's, say it again. Okay, so time and energy, because this goes faster than that, but why does this go faster than that? Okay, so it has heat, but guys, if we hold a match up to this, we know eventually this is going to go, right? What if we hold the match up to this? Does it rust any faster? No. So what's the difference? Could be surface area. Bottom line, guys, activation energy. If you drew the activation energy curves for these, which one's going to have a higher activation energy, the fire or the rusting? Because it happens faster. Guys, this is what, I mean, sort of, but generally, this is what the reaction energy diagram looks like for flame. We add a little bit of energy to get the reaction started, and then it cycles back on itself and it goes. This is what rusting looks like. The activation energy hump is so much higher that fewer of the collisions get over and the reaction happens slower. You get the idea? There you have it. So guys, we're done. In front of you, you have your homework. We will grade this on Wednesday. You have about 15 minutes. We'll grade this on Wednesday, and then we're going to do that lab on Wednesday. It's a fun lab. You'll like it. And then, guys, Friday we're going to come back and we're going to talk about a system at equilibrium and spring break. Whew.